Welcome back everyone. So in this video let us see how to find the eigenvalues and eigenvectors of a given matrix. Okay. Besides that we'll also learn how to find the inner product of some vectors. Okay. So let us start with this thing. Yeah. So the SciLab console. Okay. So as required, I have done CLC over here. I have cleared the console. Okay. So what else now is that even though the console has been cleared, the vectors are still defined, means the elements are still defined. Just see this. Okay, so if I type A and ask for the output, it gives me this matrix A which was defined before. Okay, so so keep this in mind. CLC only clears the commands, not the memory of the variables. Okay, so now I want to find the eigenvalues and eigenvectors of the square matrix. So the command basically is just eigenvalues can be easily found out using this command spec of A. Now what do you mean by spec of A? Sorry, capital A. What do you mean by spec of A? It actually gives you the spectral values of A. Spectral values are eigenvalues. I had also told you that the eigenvalues also have another name called spectral values. Okay, so that's why this thing has been defined in that sense. It's called spectral values. For physics and all, they use the name spectral values only. They don't use the word eigenvalues. Okay. So the spec of A gives you the eigenvalues of A. So these are the eigenvalues. They turned out to be complex numbers for this given matrix. Okay, so it is 9 plus I. No, sorry, it's 9. Then 9 real number it is, and then 0.5 plus something 0.866 I, and then the complex conjugate of that number. Okay. Not only that, you can also find a diagonal of this, but for finding the diagonal you have to define something more. Okay, so to get the diagonal out here, let us define the set E comma D of is equal to, okay, this is a matrix which I am defining. E comma D, its values I am going to define as spec of A, sorry, capital A. Okay, so having defined this, yeah, just use the semicolon so that I don't want the output to come straight away. So E will store the eigenvalues and D will store the diagonal matrix. So just see this now. If I ask for the output E, this gives me the eigenvectors, and this is the eigenvectors, and D gives me the diagonal matrix. Okay, so this is a diagonal matrix consisting of the eigenvalues of A. The diagonal elements are the eigenvalues, the off diagonals are 0. Okay, it's 0 plus 0 I it has been written because the entries were complex in this example. Okay, otherwise we'll just get 0 over there. Okay, if you have real numbers. Okay, so the eigenvalues are given as eigenvectors. So the first column of the matrix E defines is giving, it gives you the eigenvector corresponding to 9. Okay, the second one gives you an eigenvector corresponding to 0.5 plus something, and then 0.5 minus something. Okay, yeah, so let's go further. Let's do another example. This matrix J which was defined earlier. Okay, so this is the matrix J. So now I'll do this again. I'll call this as E1 comma D1. Okay, end of square bracket is equal to spec of J, sorry, capital J. Okay, put semicolon on because I don't want the output to come straight away. So now let me write it like that. Display and write it in the form of a sentence. The eigen values of matrix J are matrix J are end of this thing, comma, or you can use plus sign also. It is comma or plus sign, spec of G, capital G. Okay, end of bracket here. Okay, so the eigenvalues of J are this number. Okay, first eigenvalue is actually 0 over there. Okay, and then the corresponding eigenvectors I'll write down. Display the eigenvectors of J are the matrix E1. Okay, so it's printing this as this thing. Okay, so this is how we get the eigenvalues and eigenvectors of a matrix. Okay, now let us just see what will happen if I give a matrix which 3 eigenvectors are not there. Let's just do this for fun. I define a matrix U to be equal to all ones. 1, 1. Okay, this is a matrix with rank 1. Okay, so it does not have 3 distinct eigenvectors. So just see spec of U is going to be does not have 3 distinct eigenvectors. It has 0, 0, 3 as the eigenvectors. It appears 3 distinct here, but the first number is actually 3.333 to the power 10 raised to minus 16, which is 0. Okay, so only one eigenvalue and 2 are 0. Okay, so now let us do this like this. Small c comma d, and this small c comma d is equal to spec of u. Okay, I directly got the output here. Oh, this fellow had 3 distinct. This had 3 distinct eigen vectors. Okay, so it was a bad choice. At least it has given me 3 distinct eigenvectors. I don't know. It was the matrix of rank 1. My mistake. Okay, we'll have to find some other example for this where this thing fails. But never mind. So this is of how we find eigenvalues and eigenvectors of a given matrix. Okay, now let's go to the next thing what I wanted to show you all. That was this time now. What is this? Yeah, it's a very short video. So yeah, CLC I'll do. So let me define vectors like this. I have an element in R3 or Rn, whatever. I write it like this: 1 space 2 space 3. Okay, and I want to find the inner product of this. Oh wait, before that now I'll have to teach you one more command. Never mind. This is a row vector. There are some commands remaining. Yeah, so some ready-made commands I'll just give you all. So if you have size, there's a ready-made command called size of a matrix. If you talk of size of A, capital A. This tells you that A is a 3 by 3 matrix. Then also we had defined a 3 by 2 matrix sometime back. So size of M, it's 2 into 3 matrix. Okay, so you can also do size of M transpose, it's a 3 by 2 matrix. Okay, the output is coming like this, 3 space 2. Okay, so you are supposed to read it as 3 by 2. Okay, I had defined a small 2 by 2 matrix somewhere. Somewhere it was defined, but I don't remember the thing now. Here I'll find it. See, this is all the data is there now. All this entries are defined here. I'm not sure if no, it's not saved here unfortunately. I had defined a 2 by 2 matrix as something. Oh, I had not given it a name. That was the problem. It was actually M. Okay, so let's do like this. The 2 by 2 matrix were obtained by using calculating M star M transpose. So that becomes a 2 by 2 matrix, and size of M apostrophe star M, this was 3 by 3 matrix. Okay, so that's the size. Then you can also define the length command. LENGTH, this is the length of a vector R. R is a vector there, so it gives the length of the vector is 3. Okay, we had defined something called X also, no? So X was a column vector. So let us just see if we can find the length of a column vector. Yes, it gives the length of the column vector is 3. Okay, X was a 3 by 1 vector, and so this fellow is classified its length as this. Let's see what happens if we find length of a square matrix. Length of a square matrix, capital E, 9. So it's counting it as 9. So basically it tells you that there are 9 entries in this matrix C. Okay, it's not actual length of the matrix. Okay, it tells you just the count of how many entries are there in the matrix. Okay, so now some interesting commands here. That is sum of a matrix. What this does is, but before going here, let me just write what is it. Capital A, sorry. Capital A is this. So now there's a command here called sum of A. What this does, it adds up all the entries in the matrix. Okay, so sum of A gives you the sum of all entries in the matrix. Verify this, that this is true. You get 3 plus 4 is 7. Plus 2 plus 7 plus 5, that's 12. 12 in the first row. Then 3, 10 in the second row. So 22. Then 6 in the last row. Did I make a mistake? Sorry, yeah, correct it is. 22, 24, 25 and 29. Correct. Okay, next use another thing called prod. Okay, so prod of A is, it gives you the product of all entries in the matrix. Okay, so now these are some simple commands, some 4 simple commands which are there regarding matrices. So now what can we do with this commands? We can use it to calculate the inner product. So now I wish to calculate this inner product over here. So I have defined my R as 1, 2, 3, right? Just tell me what's R. 1, 2, 3. Okay, so I have defined my vector R to be 1, 2, 3, 1, 2, 3. How do you calculate the inner product of this, or rather norm of this? We first will do norm. So R dot R. Okay, so what we do? 1 into 1 plus 2 into 2 plus 3 into 3, right? Okay, so what am I doing? I'm doing term by term multiplication of R with its self. So and then I have to write down norm of R. I write it as square root of R dot R. Okay, so term by term multiplication and then square root involved here. Okay, so what should be the corresponding command over there? I should write this as sqrt of R dot wait, lots of commands are there. First to calculate R dot R. Okay, R dot R will be a matrix only. That will be 1, 1, 2, 2 and 3, 3. Right? This will be R dot R. Then you do sum of R dot R. This will give the sum of this. Sum of 1 square plus 2 square plus 3 square. Then square root of, call this people by names, A, B, and then square root of B. So this will give you the inner product of R into R. In other words, norm over here. Okay. Inner product, just define another vector, R1 and R2. Okay. And then we can do inner product over there. Okay. We'll do that also. So R is this. So let A be equal to, small a be equal to R dot R. Sorry, dot is not defined here. You have to do R dot star, term by term multiplication. Okay, and then let B be equal to sum of A. Okay, and then we want to know the square root of B. This is the norm of your vector. Okay, now if you had any other vector, say R1 is defined as 4, 7, 6. Okay, 4, 7, 6. Okay, so we can repeat the same process with that also. So do the same thing here. A, I'll redefine the variables. Okay. A1 is going to be equal to R dot star R1. Okay, so this is the thing. So B will be equal to sum of R, sum of that quantity A, sum of A sum of A1. B1 is going to be the sum of A1. Okay, this is what we get, 36, and then we find out the square root of B1, and that will give you the inner product over there. Okay, oh, inner product doesn't require the square root, no, sorry. No, inner product does require the square root. Anyways, okay, so this is about finding norms and inner products here. So this was one thing. What else remains is, there are some more ready-made commands available. So one is E, if you write down zeros. If you want to create a matrix full of zeros, or you can have various sizes, 2 cross 3 matrix full of 2 plus 3. So this zeros, see the spelling of zeros, that generates a 2 by 3 matrix of containing all zeros. Okay, there is a command even to generate a matrix full of ones, but I don't remember it. But there is a command like that. You can create a matrix full of ones. and there's a matrix RAND. Let me just check if this works. Yeah, so what RAND does, it gives you a matrix consisting of random entries, a 3 by 4 matrix consisting of random entries. Okay, so let me just see if that once is working. Not sure. This is it works. Yeah. Okay, so the command for a matrix full of ones is ones, for zeros is zero, and RAND gives you a matrix of random entries. Now, why these three commands are required is we'll be requiring at least the first command to create an empty matrix full of zeros. Okay, and then we'll add some entries into it. Okay, so that is required to when you're solving some differential equations or solving some problems, require empty matrices over there to add the solutions, to store the solutions of the differential equation. So we solve a differential equation and we store it in those locations over here. Okay, basically what we'll do is I'll replace this 0 with one solution, this 0 with another solution, and so on. Okay, random is required when you're doing certain statistical calculations and all. You require certain random numbers to just be created and solve it again. Notice that if I apply this command again, let's see the fun. RAND 3,4. I'll get a completely different matrix. If I apply it one more time, again different. Okay, so every time you try it, it gives you a different matrix. Okay, so it's completely random. Okay, so that's about this. Anything did I miss out? Let me just check if I missed out on anything. Yes, I forgot a couple of commands. So how to locate certain entries of the matrix. So if you want to access the A23 element, the element in the second row of A and then the third column of A, second row, third column, just type this, second row, third column. Yeah, so you can see this entry over here has been coming out as an output. Okay, now you can just change 3 2, you can try 4 3, you can try 3 4, you can try. No, that 4 3 entry is not defined here. No, 3 4 you can try. Okay, so try different entries here. Now if you want to print, get the output of this thing as the first row or second row, I'll say the entire second row you want to get printed. So then type A2 comma, so you fix the second row and you vary the columns. Okay, so this is the meaning of this notation. You are fixing the second row and varying the columns. So this gives you the second row as the output. Sorry. Then if you want to output the particular column of this thing, so what I'll do, I'll vary the rows and I'll fix the column. That gives me this. Okay. So this has given me the output as the third column. Okay, so in this we are done with our study on matrices. If there is anything else which I could have done, I'll explain to it a little later on. We'll make some additional videos later on. Okay, so that's all over here. Okay, so we have covered eigenvalues, then norms, then we have also done various things, and I also taught you how to create random matrices and random zero matrices and matrices full of 1. Okay, so that's all in this video. Thank you for watching. Bye bye. I have to manually switch this off.